So, review 11 has to do with normal distributions. So, a normal distribution is a bell-shaped and symmetric. Uh, it is important, though, that not all symmetric unimodal distributions are normal. So, normal distributions always have to be bell-shaped and symmetric, but not all of them that you see are going to necessarily be normal. They have an infinite base, long, flat-looking tails that cover many values but only a small portion of the area. Far out in the tails, the curve is going to drop proportionally at an ever-increasing rate. The mean and the median will be equal to each other, and they are located at the center. 2 points of inflection where the slope is the steepest. Let me draw a picture. This might be helpful. All right, so there are your long flat tails. Your mean and your median would be in the center. 2 points of inflection where the slope is the steepest would be like here and here. The distance from the mean is exactly 1 standard deviation at those places. The distance under the normal curve is measured in z-scores. Probability associated with any interval under the normal curve is equal to the proportionate area found under the curve and above the interval. And then the empirical rule, which we've talked about several times, the 68, 95, 99.7% rule. 68% of the data is within 1 standard deviation, 95% within 2, and 99.7% within 3. Using tables of the normal distribution. So, standard normal table, which is going to be provided to you on the exam, shows the area under the normal curve. Specifically, it shows the area to the left of a given point. So this is an example of the standard normal table. So you'll know that it's the standard normal table when you're going through your formulas that are given to you that day because it will say standard normal probabilities. And if you look at what's happening in the picture, it shows you the normal curve, it shows you the line, which is your z-score, and then the area to the left of that is your probability. For example, below, draw an example that shows an area of 0.889 or 49 to the left of a z-score of 112. That's different. So there is your basic curve. A z-score of 1.2 would be here. So that means that you've traveled, this is the median, you've traveled 1 standard deviation and then a piece. So 1.2. I'm going to get rid of my center line. Alright, so the area of 0.8849 to the left would be all of this. And it would be 0.8849. Because the total area under the curve is always going to be equal to 1, the area to the right, so we went to the left on this example, but the area to the right can be calculated by 1 minus the area to the left. For example, the area to the right of a z-score of negative 2.13. So if you were looking at this, you'd have your normal. That's not quite that. You'd have your normal. If you were looking at negative 2.3, if that was the center, 1 and then 2. So we'll estimate it to be about there, negative 2.13. We need to find the area to the right. So what we can do is find the associated value for the area to the left. So to do that, we would go to the table. We would go find a z of negative 2.1 and match it up with the 3 because we were doing negative 2.13. So that would be 0.0166. So here would be 0.0166, but we want this. So to get this, we would do 1 minus the 0.0166, and we would get 0.9834. Alternatively, by symmetry, we could have said that the area to the right of negative 2.13 is the same as to the left of positive 2.13, and then read the answer directly from the standard normal table. So if you did that, you could have gone and found positive. This is the continuation of the standard normal. So if positive 2.13 and got 0.9834. Either way is fine, whichever one you understand better will get you the right answer. The area between 2 points can be found by subtraction. For example, the area between the z-scores of 1.23 and 2.71. So if we were looking at standard normal table, say you've got 1.23, so that would be, there's the center, like here. And then 2.71. This is not quite right. Would be almost 3, so we'll say it's here. And you're finding this. You could go on the table to positive 1.27 or 1.23. Which is 0.8907. That would be all of this over here. So it might be helpful to write that down somewhere. And then 2.79. Or 71, 2.71. So go to 2.7 over to 1, you get 0.9966. All right, but that would be to the left of that line, so all of that. So that would take up everything from here all the way over. But you don't have to worry about the stuff that's past the 1.23. So what you can really do is do 0.9966 minus 0.8907, and that would give you 0.01 or 0.1059. Given a probability, we can use the standard normal table in reverse to find the appropriate z-score. For example, to find the z-score that has an area of 0.8982 to the left of it, we would search for the probability closest to 0.8982 in the bulk of the table and read off the corresponding z-score. So going to the standard normal table, we're looking for 0.8982. So 1.3 row starts at 0.90, so 1.2 starts at 0.88, so we're going to be looking for sure in this row. We are looking for 0.8982. So 0.8962, 0.8980, 0.9997. So the one that's closest to it would be at 1.2 and 0.7. So 1.27. To find the z-score with an area of 0.72 to the right of it, you would need to look for 1 minus 0.72 equals, did I go too far? That seems to not make sense. So anyway, to find the z-score with an area of 0.72 to the right of it, we would look for 1 minus 0.72, which is 0.28 in the bulk of the table. So going back to the table, we are looking for 0.72, or 1 minus 0.72, which is 0.28 in the bulk of the table. So it's not going to be in the positives, so let's look in the negatives. So negative 1.89, or negative 1.8 is 0.03. Negative 1.9 is looking like it might be our row. So negative, whoa, I'm way off, way off. It's 5 o'clock in the morning, I just want you to know. Alright, so you're going to be looking for 0.28, not 0.028. So 0.28. So looking in this particular area, it looks like the closest one we have is right here. That would be negative 0.6. Let's go back. Oh, these are better. Okay. So looking down here, looks like that might be the best one. So that would be negative 0.58. All right, using the calculator with areas under a normal curve. So on the TI-84, which is a calculator that you were given in class, you've got the normal CDF, which you can use. So remember, you can plug in normal CDF with your lower bound and then your upper bound, and it's going to give you the area or the probability between two z-scores, while the inverse normal gives you the area, or the inverse normal with the area gives the z-score with the given area to its left. So you could have calculated the above by using negative 1e99, which just means negative infinity to 1.2. If you did this on the calculator, you would do second bars, normal CDF, your lower at negative 1e99, your upper at 1.2, mu at 0, standard deviation at 1. Go ahead and paste, and that is going to give you 0.8849. This picture would look like this. Normal CDF with negative 2.13 to 1e99 positive infinity would look like this. So then on your calculator you could do second bars, normal CDF. This time your lower bound is going to be negative 2.13. Your upper bound is 1. Second, comma, 99. Mean is 0, standard deviation is 1. Paste. So whenever you do that, you should get 0.9834. This is an example of being between two, so a picture like this. So we do second bars, normal CDF. Our lower bound is going to be 1.23. And our upper bound is 2.71. Mean is 0, standard deviation is 1. That would round to 0.1060. Inverse normal of 0.8982 just means that you have an area of 0.982. So second vars, you're going to do inverse normal, which is option 3. The area is 0.8982. It's normal, so mean is 0, standard deviation is 1. Whenever you do that, you get 1.271. This would be the area is 0.28. So second vars, 3.28, standard deviation is 1, mean is still 0. And that gives you negative 0.58. The TI-84 also has the capability of working directly with raw scores instead of z-scores. In this case, the mean and the standard deviation must be given. So you could also do normal CDF, lower bound, upper bound, and then your mean and your standard deviation being something other than what you're given as a normal, and then inverse normal with the area, and then your mean and your standard deviation.